Welcome to this tutorial on Markov chains. Understanding the properties and characteristics of Markov chains is critical to the topic of MCMC methods. Today, I have planned to explain you not only the theoretical and mathematical underpinnings of this subject, but I am also sharing an interesting story of what led to the invention of these so-called Markov chains. I have put the timestamps in the description. So if you're not interested in the historical aspects of Markov chains, please use them to skip over to the other sections of this tutorial. That said, a very brief recap is required so that we do not forget what is it that we are after. In part 8 of this series, I had formally introduced you to the expected values and more importantly, how we can approximate them using the law of large numbers. Essentially, this law states that if you can conduct large number of trials, then your average converges towards the expected value. However, for this law to be applied, you must be able to sample from your distribution. We then discussed that your programming language or its standard library only provides support to sample from uniform distribution. And the big question was, how do we sample from non-uniform distributions? I gave an overview of 3 sampling methods that differ from each other in their respective capabilities, limitations, and use cases. However, there is one aspect that I did not deliberately talk about. And now is the time to talk about it. The sampling methods discussed so far result in what we call independent samples. What does that mean? Look here, there are 2 samples, one colored orange and other is green. As should be evident from the function, the respective plausibility of these 2 samples are quite different from each other. Sample colored orange has high chances of occurrence than the green sample. But the occurrence of one sample has no impact on the chances of occurrence of another sample. This behavior is called independent sampling. And of course, now you should wonder about what if the samples are indeed supposed to be dependent on each other. If you think about it, in quite many of the real world phenomena, the future observations have dependency on the past. The entire field of time series is based on this notion of dependence. But even more important question for us to ask is if the law of large numbers would still apply. So far, we have seen it working for sampling methods that assume the independence amongst the samples. And this, my friend, was also the controversial topic at the turn of 20th century. But before we get engulfed in the controversy, it is also imperative to quickly learn about from where and when this law of large numbers came into existence, as it is the root of debate and quarrel. And for that, I first introduce you to Jacob Bernoulli, who was the first one to give the proof of this law. You most likely have heard of Bernoulli, as there are so many things named after him. There is a Bernoulli distribution, Bernoulli trials, and you study them in the introductory courses on probability theory. As such, he did not coin this term. Instead, he called it Golden Theorem, and it was published in his book, The Art of Conjecturing. This theorem is what we now know as weak law of large numbers. Clearly, if there is a weak law, then a strong law must also exist. For our needs, it is not of utmost importance to worry about the difference. Not right now at least. That said, what is important to understand is that he proved it for the samples of binary independent variables. Now, the term law of large numbers was coined by a famous French mathematician named Poisson. The next best advancements to the proof of law of large numbers came from a great Russian mathematician named P.L. Chebyshev. Chebyshev is considered as the father of Russian mathematics, and he generalized this weak law beyond the binary random variables. Now, he was not only an extraordinary mathematician, but he was also a great teacher. And this great teacher had a great student, the hero of our story, Andrei Andreevich Markov. But this hero of ours had multiple interesting traits. To many of his fellow mathematicians and countrymen, he was a royal pain, a rude and arrogant fella who would not hesitate to criticize and humiliate them for even minor errors. He was such a colorful character that he would ask Russian Orthodox Church to excommunicate him and they would actually comply. But here is how I see him. You see, geniuses like him who are also at the same time perfectionists are often misunderstood. People like him value bluntness, accuracy, attention to detail, and straightforwardness over the rituals and conventions that our society sets as a norm. As such, most of the great scientists and mathematicians are perfectionists because truly without the obsession, it is hard to imagine the great work they do. You really have to obsess over the stuff to create great art and science. But our hero here is not just yet another perfectionist. He is an ultra perfectionist. His standards of work are at another level, and he demanded the same standards from others. And that quite many times was seen as a flaw by many of his time. He was indeed hard on many of his colleagues, but there was one of his peers whom he simply could not stand. This was a mathematician named Nekrasov, who was a theologist and a mathematician. Markov detested all that Nekrasov represented. And his quarrels with him were not just about mathematics, but they extended to the philosophy, religion, and social values. This all being said, history tends to paint people in a very binary way. They are either heroes or villains. And based on what I have gathered so far, I fail to see Nekrasov as a bad guy, not a person who intended to do harm. He had different convictions, beliefs, and values than Markov. He was definitely not in the same league as Markov, but that does not make him an evil person. However, the controversy did start because of him. You see, he published a paper in 1898 in which he claimed that independence is a necessary condition for law of large numbers. And this made Markov furious. He saw that the work of Nekrasov was severely flawed, and he took upon himself to provide a proof of applicability of law of large numbers to the variables that have dependence. He did so in sequence of papers published between 1898 and 1906, and there is a clear proof that his greatest work came into existence because of his hatred towards Nekrasov, as he talks about it in one of his letters to his friend. Oh yes, our hero, however flawed and disliked, had a dear friend, possibly the only friend. His name was Alexander Chuprov, who was a statistician and a sort of bridge between Russia and what was happening in Europe related to the work on statistics. Markov and Chuprov exchanged letters for quite many years, and there is a collection of those letters now in the form of a book. Here is one of the important letters that shows how much Markov detested Nekrasov. He is arguing with Chuprov that the work of Nekrasov is simply incorrect, and how he has now proven that independence is not a strict requirement for the law of large numbers to hold. For me, it is fascinating that the work of Markov that started because of his hatred towards Nekrasov would become fundamental in solving many problems in the modern world. And now I explain and provide the insights and associated proofs of what we now know as Markov chains. And for that, we start with a random variable x. If I put a circle around a letter, it means that it is a random variable. And random variables have distributions. X here is a discrete random variable and has 4 possible states. The plot here shows the respective plausibility of the 4 states. Now I make one modification here. I say that this is a distribution of random variable x at t equals 0. As such, a concise way of representing this fact that it is a distribution at t equals to 0 is to modify the notation of our random variable by putting a subscript of 0. This essentially conveys the same information. So this was a distribution of random variable x at t equals 0. And the next plot is showing the distribution of x at t equals 1. And here it is for t equals 2. What you must pay attention to is that the random variable x still has 4 states. It still represents or is about the same physical phenomena, but its distribution is changing with time. So the natural question to ask is what results in such a behavior? As such, this is not an unusual behavior. The distribution of random variables can easily change because of many factors and depending on what they represent. Now, I'm ignoring the external factors, but one aspect that clearly has an impact on what would be the distribution of random variable at next time step is about the realized value of random variable at the current step. For example, here I am considering that at t equals to 0, the realized or observed value of random variable x is s1, the state 1. And this would have an influence on what would be the next realized value. That said, this influence will always have uncertainty, and hence we should take help of probabilities again. We either make an hypothesis or use our domain knowledge to say that if at t equals to 0, the realized value is s1, then the probability that at t equals to 1, it will still be in s1 is 20%. Probability that at t equals to 1, it will be in state 2 is 50%, and so on for the other states. If the realized value at t equals to 0 was s2, then the probabilities of realized values at t1 will be different. These type of probabilities are called transition probabilities. Essentially, we are specifying what is the probability that S2 from t equals to 0 will transition to S3 at t equals to 1. This idea of a random variable at certain time step, depending on the previous time step, is called Markovian property. When you consider the random variable at various time steps such that at a given time step you only consider the previous time step, you create what is called a Markov chain. As such, you could depend on more than one previous time step. In that case, you would say that you have a second order or a third order Markov chain depending on the number of previous time steps you take as your dependency. However, second order, third order and so on would come with the problem of additional computation requirements. So when we say Markov chain, we are mostly referencing to the first order Markov chains. This all being said, this way of visualizing the transition probabilities of Markov chains is not very efficient. So let's look at the conventional way of visualizing how the states transition from one to another. Here I have simply drawn the states and put them in the rectangles. To indicate the possible transitions, we use arrows from one state to another state. Here we see that the probability that you will stay in state 4 is 90%. Probability that you will move from S3 to S4 is 20%. Probability that you will stay in state 3 is 30%. And here is the complete transition diagram. So this diagram is good for having a visualization of the states and their respective transition probabilities. However, if we want to use mathematics to make use of this information, then the graph is not going to be that helpful. And so we need to represent this transition diagram using another method. And that method is that of using matrices. This matrix, called transition matrix, will also capture the same information as present in the transition diagram. The matrix will always be a square matrix, that is, the number of rows and columns will always be same. In this example, the number is 4, that is the number of the possible states. And now we will fill in the values in this matrix. We first look at transition from state 1 to state 1. As per the transition diagram, we never stay in state 1, so we write a 0 here. Now look at going from state 1 to state 2. The transition probability is 0.9, so we write it in the matrix. And using the same process, we can fill up the entire matrix. The rows here represent the states that you are transitioning from, and the columns represent the states you are transitioning to. As such, using this matrix, we can now answer the same questions that we could using the transition diagram. For example, if I ask what is the transition probability of going from S3 to S2, then we will first look at the row S3, then go to column S2 and pick the value from the matrix. Let's do it one more time. We are now asking what is the transition probability of going from S2 to S4. Again, we first go to the row S2, then go to the column S4 and pick the value. And we can generalize all this process like this. We typically use I as a symbol for row number and J as a symbol for column number. The little p with subscript ij represents the element in the matrix. We'll be using these symbols heavily, so it would be a good idea to pay attention here. So essentially, using a transition matrix, you can easily answer the transition probability of moving from state at current time step to the next time step. And this leads us to asking an interesting question, and which is to find the transition probability of going from state I to state j over 2 steps. Again, remember, the transition matrix is only telling us what is the transition probability to the next time step. Here we are interested in going to the second time step. So let's sort out this by being little creative and using our knowledge of rules of probability. This is simply a change in notation. The subscript I on P is meant for the starting state, and we will bring the original conditioning after applying our tricks on simplified notation. Now I have applied the sum and product rule. The combination of these rules also result in what we call partition theorem or law of total probability. Essentially, we intend to consider all the possible states in between our starting state and the target state. If this sentence does not make sense, then you may want to watch the tutorial on rules of probability on my channel. So in this step, I bring back the original notation, that is conditioning on x at t equals to 0. Since the next state depends on the current state because of the Markov property, we can get rid of the conditioning on x at t equals to 0 in the first term. So we have the components now in one step transition form. The first term is going from x1 to x2 and the second term is going from x0 to x1. Now we can simply substitute the generalization we did earlier. That is, we replace these terms by the corresponding elements from the matrix, from the transition matrix. And I simply do some rearrangement here and finally represent them using the transition matrix. So this derivation is showing that to compute the transition probability of going from state I to state j in 2 steps, you need to multiply the transition matrix by itself and then go to the ijth element in the resulting matrix. This is interesting. For 2 steps, there is a power of 2 in our transition matrix. And now we ought to ask one more question. And you probably guessed it. We are interested now in going from state I to state j in 3 steps. I am not going to describe them in the same detail as the steps are more or less the same as before. It's just that we will use the result from previous question, that is probability of going from x0 to x2, and you can see indeed there is a pattern here. This time we have a cube of our transition matrix. 3 steps, and you can see that there is a power of 3 on the transition matrix. And therefore we can generalize to say that in order to go from state I to state j over t steps, you need to multiply your transition matrix t times by itself. So far we have discussed all things related to transitioning from one state to another over certain time steps. Now we must look at the distribution of our random variable itself and see where it fits in all the story of Markov chains. So here is our random variable with its distribution at t equals to 0. And this is how we represent this distribution. The pi here is just a symbol, a notation to indicate the distribution of random variable. I guess people in this subject use this symbol because they have run out of notations and letters. I do not know the actual reason why pi symbol is used here. Here is the corresponding n by 1 column vector. Entries in this column vector indicate the probabilities of the states. And we can generalize this notation to n states like this. Here is another generalization to say that the probability of state I of a random variable at t equals to 0 is pi subscript I. Recall, I is used for row numbers. In our column vector, we have n rows. We also use this notation to say that random variable at t equals to 0 is distributed using the row vector pi. Note that I have put t as a superscript, which is the transpose of our column vector. I use orange color for row vectors so that they can stand out. And so far, so good. Now, time to ask few questions. And the first one is about finding out the probability distribution of random variable at t equals 1. I hope you're clear that earlier we were on the quest of finding the transition probabilities, and now we are figuring it out if there is a way to find the distributions at various time steps. We again apply the sum and product rules. The first term here will be equal to the ijth element of the transition matrix, and the second term is simply the probability of x0 at state I. We worked out this notation earlier. Again, please note that this is simply a notation. Here it does not mean that value is 3.14, the value of pi. Now I do some rearrangement and finally the representation using vector matrix product. I am expecting that you have the basics of matrices and products of vectors and matrices clear to you. If not, then of course this step will not make sense. As such, I have provided you a reference to notes in the description that go over them as a refresher for you if you need them. Bottom line is that to get the distribution of random variable at time step 1, we need to multiply the distribution of random variable at t equals to 0 with the transition matrix. There is a pattern here as well. If you are interested in finding the distribution at time step 2, then you will see that in that case we will be multiplying the row vector with transition matrix squared. Here are the results. You can clearly see a pattern here. And now is the time for the most important moment in this tutorial. A significant amount of your understanding of MCMC methods, law of large numbers for dependent variables will hinge on this question. In simple words, we are asking if there is a distribution which when multiplied with the transition matrix will remain unchanged. Here is another way to say the same thing. Essentially, we are asking if there is a situation with random variable x when its distribution is not changing anymore. And the answer is yes. There does exist a type of Markov chain, a transition probability matrix for which we enter into this situation. And when it happens, we say that our random variable has reached the equilibrium distribution. I also want to clarify that here we are saying that the distribution of random variable at various time steps is now same, but this does not mean that the realized values will be same at various time steps. They will be realized or observed in accordance with their respective plausibility given by the equilibrium distribution. There is another name for equilibrium distribution and it is called stationary distribution. Now, you do have the right to start asking why are we even interested in this question. And I'm sorry, but you still must wait few more minutes for the why, here, as I need to first show you that this situation happens for the example that I picked earlier. Here is our transition diagram and the transition matrix on which we will apply what we have learned so far. I'm going to work only with the transition matrix, and we label our transition matrix as P. So here is the status at t equals to 0. I actually start with an initial guess that at t equals to 0, all the states of random variable x are equally likely. You can see that the row vector has 0.25 or 1/4 as the entries for all the states. And we have our transition matrix initialized like this. Now to calculate the distribution at t1, we simply multiply the row vector with the transition matrix, and here is the updated distribution. Let's do it for t equals to 2 as well. This time we will take the square of the transition matrix. And let it continue for few more time steps. You can start to see that the row vector is converging towards a set of values, and slowly the transition matrix is also reaching the stationarity. There are some rounding related things that are happening as I am using only 2 decimal places, but at around t equals to 20 we have reached the stationary distribution. This is very interesting. This Markov chain indeed reaches the stationary distribution after just few transitions. So for this example, we have observed an interesting phenomena. What we need to now think of is how we can utilize or exploit this kind of a behavior for approximating our intractable probability distributions or compute expected values in Bayesian inference. The big idea here is the Markov chain that has converged to a stationary distribution will enable you to visit the various states in accordance with their respective plausibility. If you recall, in the tutorial on sampling methods, I explained that in Monte Carlo methods, a general theme is to select a proxy distribution for sampling and then adjust for the fact that you have not sampled directly from your target function. Here we have observed an interesting situation of Markov chain that converged to a stationary probability distribution. And if we can somehow make this stationary probability distribution same as that of our target posterior distribution, then we can leverage the fact that in a stationary Markov chain, you get to visit the states in accordance with their plausibility. Now, this somehow of generating an artificial or simulated convert Markov chains of your random variables is the big idea behind MCMC methods. You then run your simulated stationary Markov chain multiple times, record the number of times it visits each state, and that would be your approximation of the target distribution. This is essentially the law of large numbers but applied to the variables that have dependence. But how is actually a bigger question. And it is what MCMC methods do. There are algorithms that make Markov chains approximately converge to the target probability distribution. In Bayesian inference, this target probability distribution quite often is your posterior distribution. We will study these MCMC algorithms in the next set of tutorials. I knew that. All this guy does is ask questions. Aren't you tired, man? It's been a long tutorial. No, my friend, not all Markov chains converge to the stationary distributions. So the second question is, you selected the initial state at t equals to 0. Does it matter for convergence? So the answer for that is that the Markov chains that have stationary distribution, the initial state does not matter. In a long run, it does converge. So I kind of anticipated the next question is going to be, when does the convergence happen? And this is a difficult aspect. In the toy example with limited states, we could see the convergence easily, but the real world is more complex. And indeed, as I said earlier, it is the difficult aspect of Markov chains. And I will talk more about it when I will explain various MCMC methods. But before I end this tutorial, let me show you some sample chains. The one on the left is called irreducible chain, as you do not get stuck in one state. There is always a path forward. Now, if you look at the one on the right, you can see that if you happen to get into state 2, then there is no way you will get to then visit other states, except of course the state 1. For Markov chains to converge to stationary distribution, this is one of the requirements. That is, your chain should be irreducible. And now I want to provide you a reference to the lecture notes by Dr. Rachel Fewester. She is an expert in statistical ecology and is a professor of statistics at University of Auckland in New Zealand. I saw her lecture notes when I was searching for some examples to use in this tutorial, but now I wish I had seen them when I was learning about Markov chains. It could have saved me a lot of time. I have read a decent amount of books and articles on this subject, but in my humble opinion, these notes are simply extraordinary, better than anything I have seen so far. They are comprehensive yet simple to understand. This is very well written theory coupled with great examples. If this tutorial of mine has helped you in any way, all the credit should really go to her. My only contribution is that I have simply translated her work to a different medium. So really, thank you, Professor Fewester, for these extraordinary lecture notes that you have provided. And this brings us to the end of our tutorial. This was a long tutorial, but it was necessary to have a good understanding of Markov chains to understand what is it that various MCMC methods are trying to do. There are different MCMC algorithms and they differ by how fast and accurate they can simulate these stationary Markov chains. And in the upcoming tutorials, I do intend to talk about these MCMC methods. With this, I end the tutorial for today. I hope this was helpful and useful. Please let me know in comments if you have questions and or need clarifications. I thank you for the time you have spent here and wish you good luck with your learnings. Thank you and have a good day. Bye-bye.